My name is Cody Rogers, and today I will be going through what I did for the fourth part of the sixth lab of learning the art of electronics, which was a non-inverting amplifier. So, this wrote the schematic on the on page 265 of learning the art of electronics, which is the one we are constructing now. Does not actually have the pin numbers, so I just wrote them in. Anyways, let's get a move on. Eleven times amplifier. I'm just gonna make a. I remember right. I still haven't remembered all my rules for op amps yet, or haven't learned all my rules. I guess this is the first time I've dealt with op amps, but I think that's a times 11. Hello. So I just wanted to go through where I'm connecting things and how it interacts with the analog discovery 3, because that's what we're going to spend the rest of the lab looking at. First of all, on pin 3, it is also like the non-inverting input, we are going to put the wave function generator 1. This one right here. Now on the positive power rail, which is pin 7, we are putting the 5 volts plus. And then I'm not going to try for the negative rail, but on the negative rail, we have the minus 5 volts from analog discovery 3. Now, on the output, we are, of course, putting channel 1 output. So, let's have fun looking at that. Connect this input to our wave function 1. Then turn back on our supplies. There. And turn on our scope. Yep, both are at around 0. Now, let's go to our wave generator. So, we're going to apply 200 millivolts. Let's try. Run. Go to the scope. Yeah. Channel 1 is on our output. Just check. Pin 6. Channel 2 is... Oh, I don't have channel 2 on right now. Oh, whatever. Let's hide channel 2. And I would say that we are going about 2.2 volts to minus 2.2 volts, which is what I had expected. There is our wave generator 1. So that is what I had set it. So I am, anyways, that looks like it is correct, what I expected to get. Let's read what it says we should do. So it says, it just basically try a few different things. It said to try the sine wave. Let's try a triangle wave like it tested. Yeah, that looks reasonable. Okay, let's do a few different sine waves. So we did, let's go to 20 kilohertz. Now we have to change That still looks good. Was that 20 kilohertz? Okay, now let's try 100 kilohertz. I see we're shifting a little bit now. And megahertz. Let's go to a megahertz. Yeah, now we're getting quite a shift. I think that's what I meant by slewing. Well, what else is appearing in there? Oh! Then we're not getting the same out. Like the same the same amplitude out. Let's try 500 kilohertz. Yeah, we still see about the same things. Oh no, there, that looks a bit better. What is this at? Let's take that, the 500 kilohertz. I just want to keep, let's go down to 100 kilohertz. Yeah, see, now we're almost back to where we were. Still, like, they're shifted, but yeah, it's getting, I think what they were talking about before, the thing they wanted us, or wanted me to see, was that its amplitude, its gain got hurt at high frequency. I did learn a little bit more about what a slew rate is and that type of thing. So when I was saying slewing, I think that that is what we were seeing when the amplitude got diminished. But to give a better explanation of slewing and what it means, so the slew rate of an op amp is the amount of volts per second that the output can change. So it is usually recorded in volts per microsecond. So the slower, so the fewer volts per microsecond that an op amp is recorded, then the worse it is at responding to high frequencies. And I think that is what we were seeing with this lab right now. Well, anyways, thank you for watching, and I hope you stay tuned to the next parts of this lab.